Alright, this is 2014 AP Calculus exam. Question 1. Grass clippings are placed in a bin where they decompose. For t between 0 and 30, the amount of grass clippings remaining in the bin is modeled by A of t, where A is in pounds and t is in days. Part A asks us to find the average rate of change of A of t over the interval from 0 to 30. Okay, so this is simply an application of the average rate of change formula, which is f of b minus f of a over b minus a, where a and b are the starting and ending points, right? So in this case, we'll have a of 30 minus a of 0, because we're going from t equals 0 to t equals 30, over 30 minus 0. And then 30 and 0, you can put each of those into a of t in your calculator. And then when you evaluate a of 30 minus a of 0 over 30 minus 0 in your calculator, you will get negative 0.197. Okay, and for units, we need to think about, okay, so on top here we have a of t, and the bottom we just have t, right? So a of t is measured in pounds and t is measured in days. So since we're dividing pounds in days, the units will be pounds per day. Okay, so that is the average rate of change of a of t over the interval from 0 to 30. That's part A, and this was a 1-point question. 1 point for the correct answer with units. Okay, part B. Find the value of a prime of 15. Using correct units, interpret the meaning of the value in the context of the problem. Okay, so this is just going to put it in your calculator for a prime of 15. You can set your calculator to find the derivative of a function at a certain point, right? So you'll find a prime of 15 straight in your calculator, and it comes out to be negative 0.164. Okay, and then just like for the average rate of change, this is going to be, think about it as dA dt. It's a of t on the top, t on the bottom, so it's pounds per day for the unit. And then if you think about, okay, what does this mean? Well, a of t tells us the amount of grass clippings, so a prime of t tells us how quickly a of t is changing. It's telling us how quickly the amount of grass clippings in the bin is changing. So with this information, we can say that the amount of grass clippings in the bin is decreasing at 0.164 pounds per day at t equals 15 days. Okay, this was a 2-point question. 1 point for the answer, 1 point for the explanation of the meaning. Part C. Find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the time from 0 to 30. Okay, so the amount of grass clippings in the bin, that's a of t. Okay? And then the average amount of grass clippings in the bin, that's the average. And we want these two to be equal, right? So I'll say a of t equals the average value of a of t from 0 to 30. Okay, now it's very important that you don't mix up the average value with the average rate of change. Okay, rate of change is a secant line between 2 points. The average value is the 1 over b minus a times the integral function. Right, this is the formula for the average value of a function from a to b. Okay, so we want to figure out what value of t is a of t equal to this, right? So we'll write an equation, a of t equals, and this is from 0 to 30 again, so we'll have 1 over 30 minus 0, so it's 30, times the integral from 0 to 30 of a of t dt. Okay, so this whole thing, you can put this straight in your calculator in a graph. This will go in y1 for the graph, and this will go in y2 for the graph, and you'll graph it and find the intersection point. Okay, when you find the intersection point, you can note the x value, and that's going to be the t value for the intersection point. That's going to be where the amount of grass clippings is equal to the average. And this happens at t equals 12.415. Okay? There we go. This was a 2-point question. 1 point for the average value formula, and 1 point for the correct answer. For part D, for t is greater than 30, L of t, the linear approximation to a at t equals 30, is a better model for the amount of grass clippings remaining in the bin. Use L of t to predict the time at which there will be half a pound of grass clippings remaining in the bin. Show the work that leads to your answer. Alright, so this is like a two-part question, right? First, we need to find what L of t is, and then we need to use it to find out when there's going to be half a pound of grass clippings left. Okay, so we'll start by first finding out the equation for L of t. Alright, so it's the linear approximation at t equals 30, so it's going to be like a tangent line, right? And whenever we find a tangent line, we need to always write down two things: point and slope. Okay, the point is going to be at t equals 30, we have 30 comma a of 30, right? And then the slope at that point is going to be a prime of 30. Okay, so what we're going to do now, if we have this, we can say that y minus y1 equals m times x minus x1 to get the tangent line, and we'll just plug in our point. Our point is going to be our x1, y1, and this is our m. So y, and actually instead of y, I'll say L of t. L of t minus a of 30 equals a prime of 30 times, instead of x, I'll say t, minus x1 is 30. Okay, because this is kind of like, instead of x and y, we have t and L of t, right? So that's why we have this linear approximation here. And then when we solve this for L of t, we can add a of 30 to both sides, and we'll get L of t equals a of 30 plus this whole a prime of 30 times t minus 30 thing. Okay, that's our linear approximation. We can figure out a of 30 and a prime of 30. If you plug it in your calculator, a of 30 is about 0.783, and a prime of 30 is about negative 0.056. But just for simplicity, I'll leave it as a of 30 and a prime of 30. Okay, and now we need to figure out when will there be half a pound of grass clippings remaining in the bin. Okay, so L of t tells us how much grass clippings there is left in the bin. So if I want there to be half a pound left, I'll set L of t equal to 0.5, because that's when the amount of grass clippings in the bin equals 0.5. And then if I graph this again in my calculator, this will go in y1, so this whole stuff here will go in y1, and this will go in y2, and then I find the intersection point. That's going to tell me at what t value those two are equal. So at what t value there's half a pound of grass left. And if you do that in your calculator, you get that t equals 35.054. Okay, this was a 4-point question. 2 points for correctly determining L of t, 1 point for setting it equal to 0.5, and 1 point for getting the correct answer. That concludes question number 1. Let R be the region enclosed by the graph of f of x equals this polynomial, and the horizontal line y equals 4. Find the volume of the solid generated when R is rotated about the horizontal line y equals -2. Okay, so first let's start by drawing y equals -2. It's under the x-axis, right? It's below y equals 0, so let's say something like that. That's y equals -2, okay? And then the next thing we need to do is we need to figure out the distance between this line and each of the curves that make up R. So in this case there's two curves. The first one is from -2 to here, and then the second one goes from y equals -2 up to the top. Okay, so these are the two distances. I'll call this one lowercase r because it's smaller, and this one uppercase r because it's bigger. And then now let's make an equation for each of these two variables, okay? Each of these two expressions, letters, whatever. So we'll start with big R because that's easier, okay? Big R, notice that no matter where you are on the graph, the distance from this line to this line is always going to be 6, right? Because this distance is 2, from -2 to 0 is 2, and then from 0 to 4 is 4. So the total distance is 2 plus 4, which is 6. Okay? And now for lowercase r, that's going to be a bit tricky because it varies based on x, right? So this distance is still going to be 2, but now instead of just saying it's a constant number, it's going to be based on whatever this curve is, right? And so this height is actually just f of x, right? F of x is the same as y, and it's the same as the height above the x-axis, right? So this distance here is the height, that's f of x, and this distance here is 2, so lowercase r is actually 2 plus f of x. Okay? The next thing that we need to do is we need to figure out the intersection points. So here and here, where the two curves intersect. Okay? And that's going to be done in the calculator by setting these two equal to each other. Okay? Because that's when the two curves intersect, the y values are going to be the same. So you can just say x to the fourth minus 2.3x cubed plus 4 equals 4. And if you set this in your calculator, you could do it in your calculator, you could do it by hand if you want. It's not the hardest thing to do by hand. Either way, you'll get x equals 0 and x equals 2.3. You know, actually, I feel like it might be easier to just do that by hand, because the 4's do cancel out. So, you know, whatever you feel. So you get these two coordinates. So that means here, this is x equals 0. And here, this is x equals 2.3. Okay, that's going to be important in a moment. So now, to figure out the volume of the solid, all we have to do is plug this into the formula. Just a quick reminder, the formula is pi times the integral from a to b of big R squared minus little r squared dx. And in this case, we know that big R and little r are 6 and 2 plus f of x. And a and b, those are the starting and ending x coordinates. In this case, a is 0 and b is 2.3. So we'll just plug in all of these things into our equation, going from 0 to 2.3. And we have 6 squared minus 2 plus f of x squared, like that, dx. Okay, so we have big R squared minus little r squared dx. And if this whole thing gets evaluated in the calculator, you get the volume, which is 98.868. This is a 4-point question, 1 point for the limits, 2 points for the integrand, and 1 point for the answer. Part B. Region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Find the volume of the solid. Okay, so let's see what they mean. We have this region R, and we're taking cross-sections that are perpendicular to the x-axis. So they're going up and down, right? So we're taking cross-sections like this. Okay? And each of these cross-sections is an isosceles right triangle with a leg in R. So for example, this one might go like this. Okay, this is okay, I don't know if I should even try to draw this. But maybe that's better, yeah. It's a right triangle, leg in R. And it's an isosceles right triangle. So, let's see. It's an isosceles right triangle, leg in R. So this side and this side are equal. Okay? And I want to find the volume that I get when I add up all the infinite triangles in this region R. Alright? So we'll start off with finding the area of one triangle. And to do that, first we need to figure out the area of each of these orange lines or red lines that I just drew. Okay? So to figure out this red line, we're going to use a technique similar to what we did in part A. So we know that this entire distance here from y equals 0 to y equals 4, this whole distance is 4, but I don't want this entire distance, I just want this part. So I need to subtract out this part. And remember from part A, this part is just f of x. So to get this red line, I need to do 4 minus f of x. So if I call this distance r, lowercase r, I'll say r equals 4 minus f of x. Alright, and now since I know the distance or the length of this line, I can find the area of a triangle. Because remember, the area of a triangle is just 1/2 times base times height. And in this case, since it's an isosceles right triangle, that means that the two sides are the same, so it's just 1/2 times the base squared. And my base is 4 minus f of x, so it's 1/2 times 4 minus f of x squared. Like that. Okay, so now that I have this, I can put this in my integral, Because remember, I want to take all of these right triangles and I want to add them up from 0 to 2.3. Okay, so I'll integrate from 0 to 2.3 and I'll add up all of these little areas, right? So all of these little areas, I'll add them up, dx. And if you add up all these areas using this integral, you get 3.574. And that is the volume that you get when you do this, when you add up all the triangles. This is a 3-point question, 2 points for the integrand, 1 point for the answer. The vertical line x equals k divides R into two regions with equal areas. Write, but do not solve, an equation involving integral expressions whose solution gives you the value k. Alright, so what we need to do is we're taking this region R and we're splitting it into two separate pieces, okay? So, for example, maybe we split it right here. That's probably not the right place to split it, but just go with it for now, okay? Basically, what we're saying is, if we split it in half at some point, right, at some point k, if we split it at some point, then this area, area 1, is equal to area 2. And the question is, where do we split it so that these two areas are equal? So, how do we figure that out? Well, I can say that I can write an equation for this area, I can write an equation for this area, and I can just set them equal to each other, right? So how do I figure out this area? Well, we know that this distance from here to here, just like we did in part B, that distance is going to be 4 minus f of x. Okay? So what I want to do is I want to say if I integrate 4 minus f of x from 0 to k, right? So if we're starting at 0, and we're going over to k, and I integrate f of x, that's going to give me this area. I'm adding up all the infinite little lines. That gives me this area. And I want this to be equal to this area. So if I start at k and I end at 2.3, like that. Okay, so 4 minus f of x, that's the distance. And I'm integrating the distance from 0 to k, and then from k to 2.3. And if I set them equal to each other, this will give me the value of k. If I solve this integral out, this will give me the value of k, where area 1 equals area 2. Okay? This is a 2-point question. 1 point for the integrand, which is kind of a gimme because we used the same integrand in the previous question. So hopefully you got that one. And 1 point for setting them equal to each other in the final equation. Okay? That's it for question 2. Question number 3. The function f is defined on the closed interval from -5 to 4. F consists of 3 line segments and is shown in the figure above. G is the function defined by g of x equals the definite integral from -3 to x of f of t dt. Part A asks us to find g of 3. Okay, so simply we can take 3 and plug it in for x, right? G of 3 equals the integral from -3 to 3 of f of t dt. Alright, and now what is the integral? Well, it's the area under the curve, right? So we define this area under the curve on f from -3 to 3. So I'll mark that area here, -1, -2, -3. So it's going to be all this area from -3 up to 3. Okay, so it's this green area here. Okay, so how do we figure this out? Well, it's just a combination of two triangles. So we'll just use the formula for the area of a triangle. For this big triangle, it's going to be 1/2 times the base, which is 1, 2, 3, 4, 5, times the height, which is 1, 2, 3, 4. Okay, for this little triangle, it's going to be minus because it's under the x-axis, so the area is considered negative. 1/2 times 1 times 2. Or I guess you could call it plus and then -2, whatever makes more sense to you, because it's -2. Either way, we're going to get 10 and -1, which is 9. Okay, this was a 1-point question, 1 point for the correct answer. On what open intervals contained in -5 to 4 is the graph of g both increasing and concave down? Give a reason for your answer. Okay, so let's think about what does it mean when a graph is increasing and when a graph is concave down. Okay, So we'll start with increasing. If g is increasing, well, we know that means its first derivative is positive, right? The first derivative is positive. And we're thinking, okay, what do we know about if the first derivative is positive? Well, we have a function. Let's take the first derivative of it. Okay? So we have g of x equals this integral. And then if we take the derivative of it, well, it's going to be the derivative of that integral. Okay? And you know by the fundamental theorem of calculus that this is just equal to f of x. Okay? So if since g prime of x is equal to f of x, if g prime is positive, well, that means that f is positive as well. Okay? We can go through a similar line of reasoning for when g is concave down. If g is concave down, that means its second derivative is negative, right? And since g prime of x equals f of x, I know that g double prime of x equals f prime of x, right? So if g double prime of x is negative, then f prime of x must be negative. So we know that if g is increasing and concave down, f must be positive and decreasing, because if f prime of x is negative, that means f of x is decreasing. So f of x is decreasing and positive. So we'll just go up here now and find where on this graph is f positive and decreasing. So it's going down, but it's also still above the x-axis. And there are 2 points, or 2 regions, where we see that happening, okay? We see this region here, and we see this region here, right? Here it's negative, and here it's going up. So these are the 2 regions where f of x is positive and f of x is decreasing. So in our answer, we'd say that the regions are from -5 is less than x is less than -3. That's right here. And 0 is less than x is less than 2. That's right here. Because that is where g prime of x is positive and decreasing, right? Because g prime of x is f of x. This was a 2-point question. 1 point for the answer and 1 point for the reason. The function the function h is defined by h of x equals g of x over 5x. Find h prime of 3. Alright, so we'll just use the quotient rule here. H prime of x. Alright, because that's how we find the derivative when we have functions being divided. Okay? So, how are we going to do this? Well, it's going to be the top times the derivative of the bottom. So, 5x times g prime of x, because the derivative of g of x is g prime of x, minus the top times the derivative of the bottom. And the derivative of 5x, that's just going to be 5, right? Because you have 5x to the 1, and the derivative is 1 times 5x equals 1 times 5x to the 1 minus 1, which is 5x to the 0, which is 5. Right? So this is g of x times 5, and we're dividing by the bottom squared, which is 5x whole squared. I can simplify this a little bit, and I can get 5x g prime of x minus 5g of x over 25x squared. Okay? Now all we have to do is figure out h prime of 3. Just plug in 3 into everywhere here. So I'm going to get 15 g prime of x, because 5 times 3 is 15, minus 5 g of 3 over 25 times 9, because 3 squared is 9. Okay, now we have to figure out g prime of 3 and g of 3. Well, we know that g prime of 3, sorry, g of 3, so g of 3. So g of 3, we know from part A that g of 3 is 9, right? And to figure out g prime of 3, well, we know that g prime of x equals f of x, right? So g prime of 3 equals f of 3, which is, if we go here, 1, 2, 3, Go down. It looks like it's -2, but you can be pretty sure of that because this point is 0, 0. This point is 4, -4. So the point that's in the middle is in between 0 and 4, which is 2, and in between 0 and -4, which is -2. So that's 2, -2. So then g prime of 3 is f of 3 is -2. Okay. So I'm just going to plug that into h prime of 3. So we have 15 times -2 minus 5 times 9 over 25 times 9. Okay, that's it. This was a 3-point question. 2 points for finding h prime of x, and then 1 point for finding h prime of 3. Function p is defined by p of x equals f of x squared minus x. Find the slope of the line tangent to the graph of p at the point where x equals -1. Alright, so this is the slope of the line tangent, and whenever we find anything to do with tangent lines, we always write down two things: point and slope. Right? However, this time they're only asking us for the slope, so we only want this. Right? We want this. They're not asking us for the equation, they're only asking us for the slope. So remember, the slope is the derivative at that point. So we're at x equals -1, where that's going to be p prime of -1. Okay? Well, to do that, we just take the derivative of p of x, right? So what that's going to be is that's going to be, well, first, yeah, let's do it tomorrow. Let's do p prime of x. That's going to be f prime of x squared minus x. But then, since the function inside here is another function, we have to multiply by the derivative of it by the chain rule. Okay? So we have x squared minus x, we have to multiply by the derivative of that to get 2x minus 1. Right? This is a composite function, so it's the f of g of x, right? So for these composite functions, we have to use the chain rule. Okay? F of g of x times g prime of x. So we have this, and now what we have to do now to find p prime of -1 is to plug in -1. So if we plug in -1 into here, we'll get 1 squared minus -1. So it's going to be 1 plus 1, which is 2. So we have f prime of 2 times 2 times -2 minus 1. That's going to be -3. Okay? Now to find f prime of 2, that's going to be the slope of f at 2. So here's f, and at 1, 2. So here we need to find the slope of this line segment, right? And now we're going to rely on regular old algebra 1, rise over run. Right? Rise over run. You can see that if we go down by 2, we go over by 1, right? So the rise is -2, and the run is 1, so the slope is -2. Alright? So this is f prime of 2 is -2, so this is -2 times -3, which is 6. Okay? This was a 3-point question, 2 points for finding p prime of x, and 1 point for finding p prime of -1. That's the end of question number 3. Question 4. Train A runs back and forth on an east-west section of a railroad track. The velocity, measured in meters per minute, is given by a differentiable function v sub a of t, where t is in minutes. Selected values for v sub a of t are given in the table here. Part A. Find the average acceleration of train A over the interval from 2 to 8. Okay, so we don't know much about the acceleration, but we do know stuff about the velocity, right? So let's try to figure out how to relate the acceleration and the velocity. So, the acceleration, a of t, so we know that the acceleration is the derivative of the velocity, right? So if I want to find the acceleration of train A, I have to look at the derivative of the velocity of train A. So instead of finding the average acceleration, I'll find the average of the derivative of the velocity. Okay? And of course, it's going to be over 2 to 8. So the formula for average value is 1 over b minus a times the integral from a to b of f of x dx. Okay? And so if I plug in all my stuff, I'll have 1 over 8 minus 2 is 6 times the integral from 2 to 8 of v prime sub a of t dt. Okay? And then this guy, if I integrate the derivative, they're both going to kind of cancel out, and I'll just get v sub a of t. And this is going from 2 to 8, right? It's going to be 1/6 of v sub a of 8 minus v sub a of 2. Okay? And then this is equal to 1/6. V sub a of 8 is negative 120. And v sub a of 2 is negative 100. Okay? And that is the answer for part A. This was a 1-point question, 1 point for the correct answer. Oh, and before I forget, let me also talk about the units real quick. So we're looking at acceleration, right? And we said acceleration is the derivative of velocity. It's going to be the rate of change of velocity with respect to time. And then velocity is measured in meters per minute. And then time is measured in minutes. So the units for the acceleration are meters per minute, or meters per minute squared. They didn't explicitly talk about units in the answer, but it's better to include it, I guess, because better safe than sorry. Well, I don't know. You can make your own judgment there, but whatever. Yeah, okay. This is 1-point question. They just said 1 point for the correct answer, so do with that what you will. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t, where t is between 5 and 8? Give a reason for your answer. Alright, so first thing I'm going to notice is that since v sub a of t is a differentiable function, it must be continuous, right? Because continuity is a requisite for differentiability. Okay, so v sub a of t is a continuous function. So if we want to know, okay, is it 100 meters per minute? Now if we look at t between 5 and 8, we see that v of 5 is 40, and v of 8 is negative 120, right? So if it went from 40 to negative 120, it must have passed through negative 100 on the way there, right? The only way it wouldn't is if it, like, just skipped that, if it went, like, you know, something like this, like, skip down. But this would mean it's not differentiable. So we know it's a differentiable, smooth, continuous function. That's a smooth, differentiable, continuous function, right? So it must have gone through negative 100 on going from 40 to negative 120. Must have passed through negative 100 on the way there, right? So basically, we're just I'm just explaining to you the intermediate value theorem, and so we're saying that, okay, v of 5 is greater than 120, so is greater than is negative 100, and 100 is greater than v of 8, right? That looks like a G. So we have v of 5 is greater than negative 100, that's greater than v of 8. So by the intermediate value theorem, which is basically what I was just saying, there is a time t that v of t equals negative 100. T such that v sub a of t equals negative 100. Okay? And yeah, so the 2-point question, 1 point for this part where you give the answer, and 1 point for the explanation involving the intermediate value theorem. At time t equals 2, train A's position is 300 meters east of the origin station, and the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. Use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time t equals 12. Okay, so we need to talk about position now. And so we need, just like we did in part A, we're going to relate the position with the velocity, right? And this time, we know that if we integrate the velocity from A to B, we'll get the position at B minus the position at A, right? So we know the position at 2, and we want the position at 12. So what I'm going to do is I'm going to integrate the velocity from 2 to 12. That's going to give me the position at 12 minus the position at 2. So since I want the position at 12, I'll just solve for that, and I'll get the position of 2 plus the integral from 2 to 12 of the velocity. Right? So there, you can see that's an equation for the position at time t equals 12. Now, I need to approximate this using a left-hand Riemann sum. Okay? So, let me actually, yes, we'll just do it here. So, S of 12. Now what I can do is I can replace this S of 2 with 300 because they told me in the problem that S of 2 is equal to 300. Okay? So it's equal to 300 plus this. So how do I figure this out? This Riemann sum, right? We wanted a, oh sorry, it's a trapezoidal sum, not a left sum. Trapezoidal sum. So we're going from 2 to 12, and they said 3 subintervals in the table. So those subintervals are from 2 to 5, 5 to 8, and 8 to 12. Okay? So how am I going to do this? Well, I'm going to say, okay, so for the first subinterval from 2 to 5, what I'm going to do is I'm going to take the, so since it's a trapezoidal sum, what you do for trapezoidal sums is you take the average of these two values and you multiply it by the difference in these two values. Okay? So here, the average between 100 and 40 is going to be 100 plus 40 divided by 2. So, that's in white. So, 100 plus 40 divided by 2 times the difference between the two t values, 5 minus 2 is 3, times 3 plus, and then for the next, from 5 to 8, it's the average between these two. So it's going to be 40 plus negative 120, so minus 120 over 2 times the difference in the t values, 5 to 8, 3, plus, and then 8 to 12, difference between that is 4, and the average between these is going to be negative 120 minus 50 over 2, scroll over a bit, times the difference between 8 and 12, which is 4. Okay? And then if you evaluate this entire thing in your calculator, you're going to get negative 150. Oh wait, hold on. You can use your calculator. Right, if you evaluate this using your own ability to do addition, division, and multiplication, you will get negative 150. This was a 3-point question. 1 point for getting the equation for the position at 12. 1 point for the left Riemann, I keep saying left, the trapezoidal Riemann sum, and 1 point for the correct answer. A second train, train B, travels north from the origin station. At time t, the velocity of train B is given by v sub b of t equals blah blah blah, and at time t equals 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. Okay, so this is going to be a very visual question. So let's draw this, okay? We have train A that's going back and forth, right? It's going side to side. It's going east-west. Let me use my ability to draw straight lines. There we go. It's going east and west. And then we have train B is traveling north. Okay? So we know that at time t equals 2, the position is 300 meters east of the origin station. So train A is right here. Okay? And then train B is 400 meters north. It's right here. And then we want to know the distance. We're talking about the distance between train A and train B. That's this distance here. Okay? This is 300 and this is 400. So notice right away that we have a right triangle situation. And since we're talking about the rate at which this distance is changing, this is actually a related rates problem. Okay? So what we do for related rates problems is the first thing we do is we list all the information that we know. Okay? So I'm going to say that if this distance between the origin and this point is A, and this distance is B, I'm going to call this distance C. Okay? I know that at t equals 2, A is 300, B is 400, and I actually know C, even though they don't explicitly give it to me, due to the Pythagorean theorem. This is a variation on the 3, 4, 5 triangle, right? 300, 400, 500. So c must be 500. Okay, what else do I know? Well, I know that the rate of change of the position of train A is, this is the velocity, right? The rate of change of the position. This is v sub a of t, and that's going to be at time t equals 2, that's going to be 100. Right, by the way, all this caveated at t equals 2, right? This is v sub a of t, and then if I wanted to find the derivative of the position of b, so how quickly its position is changing at time t equals 2, I need to look at v sub b of t. If I plug in 2 into there, I'll get negative 5 times 4 plus 60 times 2 plus 25, which is negative 20 plus 120 plus 25 is 125. Okay, so this is 125. Alright, so that's all the information that we know. Then now what are we looking for? We're looking at the rate at which the distance between the two trains is changing, looking at the rate of change of c. So we want dc dt. Okay, so I know that was a lot of just like restating stuff that's already in the problem, but we've done the main legwork now, and all that's left is just simple math. Okay, so now we need to think about the equation that relates all of these variables of a, b, and c. The obvious equation that's relating these three is the Pythagorean theorem. So let's write that out. A squared plus b squared equals c squared. And now, since I want to look at how quickly these things are changing with time, I'm going to take the derivative with respect to time. I'm going to get 2a dA dt plus 2b dB dt equals 2c dc dt, right? Because, for example, for this a squared part, I'm going to treat it like a normal thing with the 2 going down here and then subtracting 1 to get 2a. And then since this and this are different variables, it's implicit, so I have to add a dA dt on the end. Okay? I can cancel out all the 2's, and I'm just left with this, alright? I can solve this for dc dt. dc dt is equal to a dA dt plus b dB dt all over c. Okay, and now I have 1, 2, 3, 4, 5. I have all of these. I have all these things right here. So all I have to do now is I have to plug them in. A is 300. dA dt is 100. B is 400. dB dt is 125. C is 500. Okay, so I can simplify this a little bit. I'll cross out some of the zeros. Right, so I'll get 3 times 100, which is 300, plus 125 times 4, which is 500, over 5, which is 800 over 5, which is 160. I can also do 300 divided by 5 is 60, plus 500 divided by 5 is 100, which is 160 meters per minute. Okay, there we go. Whew. That was a problem, right? That was the rate at which the distance between train A and train B is changing at time t equals 2. This was a 2-point question. 1 point for successfully taking the derivative of this equation, and 1 point for the correct answer. Notice we didn't get any problems for this main setting up part, but notice how easy it made the problem near the end, right? If we didn't do this earlier on, we'd have to go back and search through the problem and find every single one of these values. Okay, so that's it. That's the end of question 4. Let's move on to question 5. So the twice differentiable functions f and g are defined for all numbers x. Values of f, f prime, g, and g prime for various values of x are given in the table above. Part A asks us to find the x-coordinate of each relative minimum of f on the interval from -2 to 3 and justify our answers. Okay, so we want to find the relative minimum of f, right? So think about what does it mean when f has a relative minimum? Okay, well, if f has a relative minimum, what that means is that f prime goes from negative to positive. Okay, so f has relative minimum, f prime goes from negative to positive, right? If you have a graph like this, the relative minimum is here, and the derivative is negative here, positive here, right? So we need to find on our table, where does f prime switch from negative to positive? And let's go to f prime, and let's look here. We have negative, negative, and positive. So you can see at x equals 1, that's where we have a switch from negative to positive. So that's where f has a relative minimum. Okay, so they want us to justify, so you'd write out f prime switches from negative to positive at x equals 1, so f has a relative minimum at x equals 1. This was a 1-point question, 1 point for the correct answer. Part B asks us, explain why there must be a value c, where c is between negative 1 and 1, such that f double prime of c equals 0. Okay, so this is kind of clearly a mean value theorem question, right? Where they're asking us for the average rate of change of f prime, right? Because remember, f double prime is actually just nothing but the derivative of f prime, right? So if the average rate of change of f prime of x across negative 1 to 1 is equal to 0, and f prime of x meets the conditions to even apply the mean value theorem in the first place, then that's the way we can conclude that there must be some value c such that f double prime of c is equal to 0. Okay, so the first thing we need to do here is we need to look at f prime of x and say, okay, does f prime of x meet the conditions? And by meet the conditions, I mean, is it continuous? Okay, so is f prime of x continuous? Well, let's see here. We know that f is twice differentiable, right? So you can take the derivative of f prime. So f prime, it is differentiable. And for a function to be differentiable, it has to be continuous. So if it's differentiable, then we know that f prime is continuous, right? So we have our explanation here to show that f prime of x is differentiable and continuous, so it meets the requirement for us to even apply the mean value theorem. Okay, so now what we're going to do is we're going to find the average rate of change of f prime of x. So that's going to be, so from negative 1 to 1, it's going to be f prime of 1 minus f prime of negative 1 minus 1 minus negative 1. Remember, it's f prime of b minus f prime of a over b minus a, right? That's the formula here. So what this is going to be, it's going to be, so what is f prime of 1 and negative 1? So f prime of 1 is 0, and negative 1 is 0. So it's going to be 0 minus 0 over 2, which is 0. Okay? So as you can see, since the average rate of change is equal to 0, then we know that there must be one value c, at least one value c, where the second derivative is equal to 0 as well. Okay, so you can say, for explanation, by the mean value theorem, there is at least one value c, where c is between negative 1 and 1, such that f double prime of c is equal to 0. This was a 2-point question, 1 point for correctly finding that f prime of 1 minus f prime of negative 1 equals 0 minus 0, and then the 2nd point for the correct answer and explanation. Part C. The function h is defined by h of x equals ln f of x. Find h prime of 3 and show the computations that lead to your answer. Okay, easy enough. So all we have to do is take the derivative of this function and plug in 3 in for x. Okay, so let's find h prime of x first. Okay, so we're going to start by, since there's multiple functions here, we're going to start on the outside and work our way in. Okay, so first start with the natural log part. The derivative of natural log of anything is 1 over that thing. So here, the first thing we'll do is we'll say 1 over f of x. Right, ln of f of x, 1 over f of x. And ln of something, 1 over that thing. And then now, we have to multiply by the derivative of the inside function. The inside function was f of x. So we have to multiply this by the derivative of that, which is f prime of x. Okay? So h prime of x is equal to f prime of x over f of x. So h prime of 3 must be equal to f prime of 3 over f of 3. Okay? Now let's go up and find f prime of 3 and f of 3. F prime of 3 is 1/2 and f of 3 is 7. So this is equal to 1/2 over 7, which is 1/2 times 1 over 7, which is 1 over 14. Okay? This was a 3-point question. 2 points for successfully taking the derivative of h of x to get h prime of x, and 1 point for finding the correct value of h prime of 3. Part D. Evaluate the definite integral from -2 to 3 of f prime of g of x times g prime of x dx. Okay, so whenever we're evaluating these type of integrals, you can see here there's a function here and its derivative. So when we see a function and its derivative and we want to take this integral, the first thing that should come into your mind is u substitution. Okay, so what we're going to do to evaluate this integral, let me rewrite it down here. We're going to do a u substitution with u equal to g of x. So we'll say u equals g of x, and then du dx equals g prime of x. So du equals g prime of x dx. Okay, so this entire thing, g prime of x dx, I can replace that with du. Okay, so I'll have the integral of f prime of, remember, g of x is equal to u, so we'll say f prime of u, and then instead of g prime of x dx, I'll say du. Okay, and now instead of -2 and 3, I'm going to take -2 and 3 and plug them into x in this expression here. So I'll have g of -2 and g of 3. Okay, so if I evaluate this integral, I'll have f of x, right, because the integral of f prime of x, or yeah, the integral of f prime of u is just going to be f of u, because the derivative and the integral sort of cancel out as per the fundamental theorem of calculus, so we're just left with f of u. Okay, and then now we can look at what g of -2 and g of 3 are. Indeed, here if we go to -2 and we go to g of x, g of -2 is -1, and then g of +3 is +1. So instead of going from -2 to 3, we'll be going from -1 to 1. Okay, so now if we plug in our numbers, we'll have f of 1 minus f of -1. Okay, so how do we figure this out? Well, now we have f of x, and we have 1 and -1, right? So to find out f of 1 minus f of -1, we know f of 1 is 2, f of -1 is +8, so this is going to be equal to 2 minus 8, which is -6. Okay, and that's it. This was a 3-point question, 2 points for successfully taking the antiderivative using the fundamental theorem of calculus, and 1 point for the correct final answer. That concludes question number 5. Question 6. Consider the differential equation dy dx equals 3 minus y cosine x. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 0 equals 1. The function f is defined for all real numbers. Part A. A portion of the slope field is given below. Sketch the solution curve through the point 0, 1. Okay, so they're giving me this. I just need to find 0, 1 and sketch the solution that goes through it. Okay, so first off, we're going to start by finding the point 0, 1. Okay, so 0, 1 is 0 here, 1 here, that's right here, okay, because each point is like 1, right? So now all I have to do is follow the curve and just go with the flow, pretty much. Okay, so let's start with here. It's going up, 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 and then stops and it goes kind of down, right? And then here, it goes down, 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 really down, and then it's less down, and then up, and up, and up, and up. Right, okay, there we go. Alright, that was the solution curve that goes through 0, 1. That was a 1-point question, 1 point for the correct curve. Alright, part B. Write an equation for the line tangent to the solution curve in part A at the point 0, 1, and use that equation to approximate f of 0.2. As you can see, by the way, I've gotten rid of the graph because it was a little bit unwieldy, you know. So, write an equation for the tangent line. So whenever you see that when they ask you to write an equation for the tangent line, you always have to write down 2 words. Okay, point and slope. Here they were nice, they gave us the point, it's 0, 1. Okay, slope, well, slope is the derivative at the point that they give you. So since we have a function for the derivative, we have dy dx, all we have to do is find the derivative at the point 0, 1. So if we plug in 0, 1 into here, we'll get 3 minus 1, because 1 is going in for y. And then cosine x, we'll have plug in 0 in for x, so we'll get cosine of 0. Okay, so 3 minus 1 is 2, and cosine of 0 is equal to 1. So this is actually just 2 times 1, which is 2. So now we have the point and the slope, so we can put these together and get our equation for the tangent line. Okay, so following the normal standard, y minus y1, so y minus y1 is 1, equals m is 2, times x minus x1, that's x minus 0. And if you want to simplify this a bit, this part just becomes 2x, and I can add 1 to both sides, and I'll get y equals 2x plus 1. Okay, that's my tangent line. And if I want to use this to approximate f of 0.2, it's going to be approximately equal to, so I'm just going to take 0.2 and I'm going to plug it in for x. So 2 times 0.2 plus 1, 2 times 0.2 is 0.4, plus 1, that's equal to 1.4. Okay, this was a 2-point question, 1 point for the tangent line, 1 point for the approximation of f of 0.2. Part C, find y equals f of x, the particular solution to the differential equation with the initial condition f of 0 equals 1. Okay, so we have our differential equation, dy dx equals 3 minus y cosine x, right? And so what we need to do is we need to solve this for y equals f of x, okay? So the first thing that we're going to do is we're going to take all our y's and shove them on one side, and all the x's and shove them on the other side. So we'll take this 3 minus y, we'll bring it down, and we'll get 1 over 3 minus y dy equals, bring the dx, bring it over there, cosine of x dx, okay? Now that we have this, I can go ahead and integrate both sides. You can see it's already set up nicely with the dy and the dx, right? So, what do I get when I integrate? Well, the integral of 1 over 3 minus y, you can do a u substitution and get u equals 3 minus y if you'd like, but a much faster way to know that 1 over something is ln of that thing when you take the integral of it, but since there's a negative here for the coefficient, you just have to put a negative in front, okay? So, it's going to be negative ln of 3 minus y. Again, if you did a u substitution, you get the same thing. It's just that you have to divide whatever your answer is by this coefficient. In this case, the coefficient is negative 1, so we have a negative 1 there. And then here, integral of cosine of x, well, that's just from memory sine of x, okay? And then for all these questions, we'll have to include a plus c, of course. And now we can get on to the job of solving this for y, okay? So the first thing I'm going to do is I'm going to take the negative and bring it over to the other side. So we'll get ln of 3 minus y equals negative sine of x plus c. This plus c, it doesn't really change when you multiply it by something or when you put a negative in front of it. C just represents a constant. It might change, with the value of c might change from step to step, but all that matters is that it is some constant number and not a variable, okay? So next thing here is we need to get rid of the natural log. So we'll take e and put it as the base for both of these expressions, okay? So here the e and the natural log will cancel out, and I'll just get 3 minus y. And then here, I'll get e to the negative sine of x plus c. Alright, I'm going to just solve this for y, so I'll add plus y to both sides, and I'll subtract e to the negative, e to the whatever all that stuff is over here. So we'll get y equals e to the, ey equals 3 minus e to the negative sine of x plus c. Okay, and I can split this up now, this e to the negative sine of x plus c, because remember, if I have anything that's like e to the a plus b, it's equal to e to the a times e to the b. That's the property of exponents. So I can split this up, and I can say y equals 3 minus e to the negative sine of x times e to the c. Okay, and remember, e to the c is just another constant, right? So what I can do is I can treat it like just a constant and say 3 minus c e to the negative sine of x. Obviously, the c and this c are different numbers, but again, what's important is that they're both constants. So now we've solved it for y, but we're not quite done. We still have a c, and that's like a constant, but we need to figure out the value of the constant. So to do that, we're going to use the initial condition f of 0 equals 1. I'm going to take that, plug it into here. So now we're going to use the initial condition f of 0 equals 1. That's the point 0, comma 1. Because I'll plug in 0 in for x, I'll plug in 1 in for y, and I'll get 1 equals 3 minus c e to the negative sine of 0. Okay? Sine of 0 is 0. Negative sine of 0 is also 0. So this just becomes 0. It's exponent. Okay? E to the 0 is 1. So this just becomes 1 equals 3 minus c. And then that means c equals 3 minus 1, which is 2. Okay? So now we can take my expression here. I'll just plug in c equals 2. So y equals 3 minus 2 e to the negative sine of x. Okay. And with that, we're done. This was a 6-point question. 1 point for separating the variables, 1 point for taking the integral, 2 points for taking the integral. So 1 point for separating the variables, 2 points for taking the integral, 1 point for including a plus c, 1 point for using the initial condition, and 1 point for the correct final answer. That concludes question 6, and with that concludes the 2014 AP Calculus exam. I hope you found this video helpful. Like and subscribe, and I'll see you next time. Goodbye.